Welcome to the Deep Dive. Today we're going deep into number theory, exploring a really cool concept, representing integers as the sum of two squares. We'll be using the OEIS as our guide. Specifically, entry A0000008. We'll uncover some really cool patterns and gain some surprising insights about numbers along the way.
It really is amazing. Such a simple idea. Like, can a number be expressed as the sum of two squares leads to such a rich mathematical world?
I know, right? It's really wild. So to make this a little more concrete, the OEIS entry starts with an example,
Yeah.
A35. What does that even mean?
So it means if we look at all the whole numbers less than or equal to 2 to the power of 3, which is 8, there are exactly 5 of them that can be written as the sum of two squares.
Okay.
1, 2, 4, 5, and 8.
Okay, I see. Like 5 can be represented as 1 squared plus 2 squared. But what's so special about those 5 numbers? Why can they be represented this way when other numbers can't?
Well, that's where things get really interesting. It turns out there's a deeper pattern, and it's connected to the world of lattices.
Lattices, like those garden trellises you see.
Not exactly. In mathematics, a lattice is a grid of points, arranged in a very specific pattern. Imagine the intersections on graph paper. That's your square lattice. Now, there are other types of lattices, like hexagonal lattices. These look kind of like a honeycomb.
Okay, I can picture that. But how do lattices connect to representing numbers as sums of squares?
Well, the distribution of numbers that can be expressed as the sum of two squares, it's actually closely linked to the geometry of these lattices. There's a visual component to this seemingly abstract number theory concept.
Oh, wow. So it's not just equations and calculations. There's a visual, like geometric aspect to it as well.
Absolutely. And this connection between number theory and geometry, that's where things get really exciting.
This OEIS entry also mentions a formula for calculating AN, which is the number of integers that fit this criteria. For a given n, what can you tell us about that formula?
It is a bit technical, but essentially it gives us a way to calculate the value of AN without having to check every single integer. And what's really fascinating is that it involves a concept called the Gauss circle problem.
The Gauss circle problem. That sounds intriguing. What is that all about?
So imagine you're throwing darts at a dartboard. The Gauss circle problem basically asks, how many darts land within a circle of a given radius drawn on the dartboard? It's a seemingly simple question, but it actually has really profound implications in number theory.
So we're talking about counting darts on a dartboard. How does that relate to the sum of squares problem?
Well, it turns out that the distribution of numbers that can be represented as the sum of two squares, it's actually reflected in the distribution of those darts within the circle. The more darts that land within the circle, the more numbers can be expressed as the sum of two squares. It's like these two seemingly different problems are actually two sides of the same coin.
Wow. That's a fascinating connection. It's amazing how these mathematical concepts intertwine like that.
Exactly. It just speaks to the beauty and interconnectedness of math.
Now, before we move on, I'm curious about something. This OEIS entry also mentions various programming languages used to generate the sequence, like Mathematica and Haskell. What's the significance of that?
It highlights the fact that you don't always need pen and paper to explore number theory. We can use computational tools to experiment, visualize, and discover new patterns. It makes these concepts much more accessible to a wider audience.
I love that. Technology can really open up these mathematical explorations for so many people. But before we get too carried away, let's take a step back and recap what we've learned so far.
Sure. So we've seen this simple question of whether a number can be represented as the sum of two squares leads to some really surprising connections with geometry, computational tools, and we've only just scratched the surface. There are so many more layers to this.
I can't wait to peel back those layers. But before we do, let's take a short pause. When we come back, we'll delve even deeper into the fascinating world of numbers represented as sums of squares.
Welcome back to our deep dive into the world of numbers represented as the sum of two squares. Before the break, we were starting to uncover that surprising connection between this number theory concept and the Gauss circle problem. It's amazing how a simple question about counting points inside a circle on a dartboard can actually have deep implications for understanding the properties of numbers.
I know. I'm still trying to wrap my head around that connection. What is it about the numbers that can be represented as the sum of two squares that makes them so special? Why do they seem to cluster in a particular way when we visualize them on a lattice?
It all comes down to the distances between those lattice points and the origin of the grid. Remember how we were talking about square lattices having points arranged in squares? Well, when we calculate the squared distance from a lattice point to the origin using the Pythagorean theorem, those distances are always integers.
Right, the Pythagorean theorem. A squared plus b squared equals c squared. So we think of a and b as the coordinates of a lattice point. Then c squared would represent the squared distance from that point to the origin at 0, 0.
Exactly. And here's the key insight. Numbers that can be expressed as the sum of two squares, they correspond to those squared distances on the lattice. They're the c squared values in our Pythagorean equation.
So the numbers that work for our sum of squares problem are those that represent the squared distances from lattice points to the origin. That's a pretty neat visual way to think about it.
It is, and it helps explain why some numbers show up more frequently than others. Imagine drawing circles of increasing radii, all centered at the origin of our lattice. The number of lattice points that fall within each circle is directly related to how many integers can be expressed as the sum of two squares up to a certain value.
Okay, that makes sense. The bigger the circle, the more lattice points it covers, and the more c squared values we have, which translates to more numbers that can be expressed as the sum of two squares.
You got it. And this is where the Gauss circle problem comes in. Gauss was really interested in understanding the relationship between the area of a circle and the number of lattice points it contains. And his work actually gives us insights into the distribution and density of numbers that can be represented as the sum of two squares.
So Gauss's work on a seemingly geometric problem helps us understand this number theory concept. It's another cool connection. I love how these different areas of mathematics weave together like this.
It's truly remarkable, and it shows just how interconnected mathematical ideas really are. Now, before we get too lost in the weeds, let's circle back to a concept we mentioned earlier. The OEIS entry's reference to sequence A0001481.
Right. That sequence focused on the number of ways to represent a given integer as the sum of two squares, not just whether it's possible.
Exactly. Sequence A0000011 provides a more granular perspective on this problem. So while our original sequence, 00000 square, told us how many integers less than 2 to the n could be represented as the sum of two squares, this new sequence tells us how many different ways a specific number can be expressed in that form.
So it's like going from a yes or no answer to a how many answer. That adds a whole new layer of complexity. Can you give us an example?
Absolutely. Let's take the number 25. We can represent it as 3 squared plus 4 squared, but we can also represent it as 4 squared plus 3 squared, or even as 5 squared plus 0 squared.
Oh, I see. So while 25 can definitely be expressed as the sum of two squares, sequence A0001481 would tell us that there are multiple ways to do so, taking into account the order of the squares.
Precisely. And the number of representations can vary wildly depending on the number. Some numbers only have 1 or 2 representations, while others have dozens or even hundreds.
Wow. That's incredible. It's like each number has its own unique fingerprint when it comes to representing it as the sum of two squares.
That's a great way to put it. And studying these fingerprints can reveal even more intricate patterns and relationships in the world of numbers.
This is all so fascinating. I'm also starting to realize how deep this rabbit hole goes.
Yeah.
There's so much to explore.
You're telling me. That's what makes number theory so captivating. It's a field full of surprises and endless avenues for exploration. Even a seemingly simple concept like the sum of squares can lead to profound mathematical insights.
This has been an incredibly eye-opening journey so far. We've uncovered connections to geometry, explored different sequences in the OEIS, and even touched upon the historical work of Gauss. What's next on our agenda for this deep dive?
Well, we focused a lot on the how, like how to represent numbers as sums of squares and the patterns that emerge. But what about the why? Why are some numbers amenable to this representation while others are not? That's a question that has intrigued mathematicians for centuries. And it leads us to some truly elegant and powerful theorems in number theory.
Okay, now you've really got me curious. But before we dive into the why, let's take a final pause to gather our thoughts. When we come back, we'll wrap up our exploration of numbers represented as sums of squares with some insights into the underlying reasons behind these fascinating patterns. Welcome back to the Deep Dive. We've been on this incredible journey exploring those numbers that can be expressed as the sum of two squares. We've talked about lattices and geometry, even the work of Gauss. But before we wrap things up, you mentioned we get into the why. Why can some numbers be represented this way while others just can't?
Yeah, it's a question that's kept mathematicians busy for ages. And the answer, Well, it's hidden in a beautiful mix of prime numbers and something called modular arithmetic.
Prime numbers and modular arithmetic. Those sound a little intimidating, to be honest. Can we break those down a bit?
Sure thing. So first up, prime numbers. They're like the Lego blocks of all the other whole numbers. A prime number, it's a whole number, bigger than 1, that can only be divided evenly by itself in 1, like 2, 3, 5, 7, 11. They're picky.
Oh, right. I remember those from way back. Prime numbers, the ones that play by their own rules. Divisible only by themselves and 1.
Exactly. Now, modular arithmetic, it might sound all fancy, but it's something you use every day without even thinking about it. Think of a clock. It's 13 o'clock. But we don't say 13 o'clock, do we?
No, we say it's 1 o'clock. We just start counting over again after we hit 12.
That's modular arithmetic. It's like you're wrapping the whole number line around a circle, and all you care about is what's left over the remainder after you've gone around a bunch of times. Like with the clock, the number is 12.
Okay, I'm starting to get it. But how do these prime numbers and this clock thing connect to our sum of squares problem?
Well, there's a very specific type of prime number that's super important here. Primes that leave a remainder of 1 when you divide them by 4, like 5, 13, 17, they all work that way.
Primes that are 1 more than a multiple of 4.
Right.
Got it. But why are they so special in this whole thing?
Get this. A number can only be expressed as the sum of two squares if and only if every prime number in its factorization that leaves a remainder of 3 when divided by 4 occurs an even number of times.
Whoa, hold on. That's a mouthful. Can you maybe give us an example to make it clear?
Of course. Let's look at the number 12. When you break it down into its prime factors, it's 2 times 2 times 3. See how 3 leaves a remainder of 3 when you divide by 4, and it only shows up once. That means 12 can't be written as the sum of two squares.
Okay, I see what you mean. So if a number has a prime factor, like 3 or 7, that leaves a remainder of 3 when you divide it by 4, it has to show up an even number of times for that number to work as a sum of two squares.
Exactly. Now let's think about 20. It's 2 times 2 times 5, right? Now 2 and 5, they both leave a remainder of 1 when divided by 4, but that's not what we're focusing on. The important thing, there aren't any primes in that breakdown that leave a remainder of 3 when you divide by 4. So 20 can be expressed as the sum of two squares, and it is. 4 squared plus 2 squared.
Wow, that's just amazing. So whether a number can be written as the sum of two squares comes down to this dance between prime numbers and what's left over when they're divided by 4.
Isn't it neat? It's like number theory is showing us these hidden patterns, these connections, in a world that seems full of random numbers. And it gets even more interesting. This idea, it pops up in advanced math stuff like algebraic number theory, and even in things like cryptography.
Wow, it's incredible how something so basic can be so powerful and have so many uses.
Really is. And that's what makes exploring math so cool. You never know what you'll find just by asking a simple question.
This deep dive into the world of sums of squares has been incredible. We started with a basic question, explored those fascinating lattices, and discovered all these amazing links to prime numbers and modular arithmetic.
And we saw how even the most abstract math ideas can have real-world uses.
A huge thank you for guiding us on this journey. It's exactly what our listeners love, finding the beauty and complexity in the world of math.
Happy to be here. And remember, this is just the start. There's a whole universe of number theory out there waiting to be explored.
So, to all our listeners, stay curious, keep exploring, and never stop asking why. Until next time, happy calculating.